Welcome to the Networking Fundamentals module of the Networking Fundamentals for Industrial Control Systems course. The goal of this course is to enable learners to assimilate the information that is presented in further training courses, such as managing industrial networks with Cisco networking technologies. As an operations technician, you may have the question of, what do I need to know to support my network? Fortunately, regardless of the size and complexity of the network, the starting point for learning to support a network is the same. This course is intended to be that starting point and provides the foundational knowledge necessary to understand and learn how to support a basic switched and routed network. This module presents a high-level overview of the characteristics, components, and protocols that make up a network. As a network operator, understanding these concepts to facilitate day-to-day operations and troubleshooting tasks is important. After completing this module, you will be able to describe the elements that comprise a network at a high level and also identify the functions of data processing and data transport. In this lesson, we will introduce and describe the concepts and components of a network, as well as explore the roles for moving data from system to system. We will also explore the relationship between physical and logical topologies. A network is a connected collection of devices and systems such as computers, servers, smartphones, and even industrial equipment, which can communicate with each other. Networks carry data in many types of environments, including homes, small businesses, and large enterprises. Large enterprise networks may have a number of locations that need to communicate with each other. Based on where workers are situated, these locations are as follows. A main office, for example, is a site where everyone is connected via a network and where most corporate information is located. A main office can have hundreds or even thousands of people who depend on network access to do their jobs. The main office may include a data center or an industrial operation in addition to corporate offices. A main office may use several connected networks that can span many floors in an office building or cover a campus that contains several buildings. Various remote access locations use networks to connect to the main office or to each other. For example, off-site data centers can be used for shared access to data resources, cloud computing, or disaster recovery. Access to these resources is through remote connections to the corporate network. For corporations involved in the automation industry and similar businesses, manufacturing facilities may be located at a distance from the main corporate campus for various reasons. These locations would use the network to exchange information with the main office. In branch offices, smaller groups of people work and communicate with each other via a network. Although some corporate information may be stored at a branch office, these offices are more likely to have local network resources, such as printers, but they must access information directly from the main office. When individuals work from home, the location is called a home office. Home office workers often require on-demand connections to the main office or branch offices to access information or to use network resources such as file servers. Mobile users connect to the main office network while at the main office, at the branch office, or traveling. The location of the mobile users determine their network access requirements. You may use a network in your home office to communicate via the internet to locate information, place orders for merchandise, and send messages to friends. You may also have a small office that is set up with a network that connects other computers and printers in the office. Also, you may work at a large enterprise with many computers, printers, storage devices, and servers that are used to communicate and store information from many departments over large geographic areas. There are four major categories of physical components in a computer network. Those include endpoints, interconnections, switches, and routers. Endpoints in the network can be computers, IP phones, intrusion sensors, wireless devices such as tablets, and even robotic equipment. They send and receive data. Printers and servers are also endpoints in the network. The interconnections consist of components that provide a means for data to travel from one point to another point in the network. Interconnections include components such as network interfaces, which translate computer data into a format that can be transmitted over the local network. Network media, such as cables or wireless media, which provides the means by which signals are transmitted between network devices. And connectors, which provide the connection point for the media. Switches are devices that provide network attachments to the end systems and provide intelligent switching of the data within the local network. Routers interconnect networks and choose the best paths between networks. Applications can affect network performance, and conversely, network performance can affect applications. Here, the common interactions between user applications and the network are shown, though keep in mind that the user may be another endpoint running an application program as opposed to a human being using an application. Historically, when considering the interaction between the network and the application that ran on the network, bandwidth was the main concern. Batch applications such as FTP, TFTP, and inventory updates were initiated by a user and then ran to completion by the software with no further direct human interaction. For batch applications, bandwidth was important, but not critical as long as the time needed for completion was not excessive. Interactive applications such as inventory inquiries and database updates required more human interaction. Bandwidth became more important because users became impatient with slow responses. The user would request some type of information from the server and then wait for a reply. However, because response time was more dependent on the server than on the network, bandwidth was still not critical. Instant messaging, machine-to-machine, and also some e-commerce transactions, such as point-of-sale transactions, also fit into this category. In most cases, quality of service features could overcome bandwidth limitations by giving interactive applications preference over batch applications. Like interactive applications, real-time applications, such as voice over IP, and video applications involve human interaction. Because of the amount of information that is transmitted, bandwidth has become critical. In addition, because these applications are time critical, latency or delay through the network is critical. Variations in the amount of latency can affect the network. Not only is sufficient bandwidth mandatory, quality of service is mandatory. Voice over IP and video applications must be given the highest priority. Today, voice over IP is promoted as a way for organizations to save money and is said to be as easy as installing a voice over IP router into the network. While the benefits of voice over IP are easily realized in the home network, voice over IP can result in a disaster in a small office network. Simply installing a voice over IP router in a network does not ensure sufficient bandwidth, nor does the installation provide a proper QoS scheme. Applications that worked correctly in the past may begin to run so slowly that they are unusable when someone is on the phone. Additionally, voice quality may be poor. You can overcome both of these issues, bandwidth and quality of service, with good network design. You can describe a network according to performance and structure. In networks, there are physical and logical topologies. The physical topology is the arrangement of the cables, network devices, and end systems. The logical topology is the path over which the data is transferred in a network. For example, a physical topology describes how the network devices are actually interconnected with wires and cables. A logical topology describes how the network devices appear connected to network users. Speed is a measure of the data rate in bits per second of a given link in the network. Cost indicates the general expense for the purchasing of network components and installation and maintenance of the network. Security indicates how protected the network is, including the information that is transmitted over the network. The subject of security is important, and techniques and practices are constantly evolving. You should consider security whenever you take actions that affect the network. Availability is a measure of the time that the network will be available for use when availability is required. For networks that are meant to be used 24 hours a day, 7 days a week, 365 days a year, availability is calculated by dividing the time that is actually available by the total time in a year and then multiplying by 100 to get the percentage. Scalability indicates how easily the network can accommodate more users and data transmission requirements. If you design and optimize a network for only the current requirements, scalability can be very expensive and difficult to meet new needs when the network grows. Reliability indicates the dependability of the components that make up the network, such as the routers and switches, PCs, and servers. Reliability is often measured as a probability of failure or as a mean time between failures. These characteristics and attributes provide a means to compare various networking solutions. In addition to the general characteristics of the network just mentioned, There is the additional characteristic of how the endpoints in the network relate to each other and the nature of their data exchange. There are three main types of endpoint interactions, which define a network. In a peer-to-peer relationship, the two independent PCs can exchange files directly with each other. A good example of this would be ad hoc wireless devices. In a client-server relationship, the client machine is accessing services from the server. For example, in the relationship between a file server and a desktop PC, the desktop PC accesses files stored on the departmental server for sharing in the office environment, and then makes use of the data and uploads it afterwards to the server for storage. A distributed process is one in which two or more machines may take part in a shared process or transaction. A good example of this would be the interaction between a point-of-sale terminal at a local retail store performing the sale transaction during the course of a business day and getting a credit card approval from a banking system. Then the local store mini-computer uploads the activity for the day to the corporate headquarters and the banking mainframe at night. Each type of network has a physical and a logical topology. The physical topology of a network refers to the physical layout of the devices and cabling. You must match the appropriate physical topology to the type of cabling that you will install, such as twisted pair, coaxial, or fiber. Understanding the type of cabling that is used is important in understanding each type of physical topology. The primary categories of physical topologies are bus, star, mesh, ring, and tree. In early bus topologies, computers and other network devices were cabled together in a line using coaxial cable. Modern bus topologies establish the bus in a hardware device and connect the host devices to the bus using twisted pair wiring. A star topology has a central cabling device that connects the computers and other network devices together. The physical connection is commonly made using twisted pair wiring. In a mesh topology, every network device is cabled with many others. Redundant links offer reliability and self-healing. The physical connection is commonly made using fiber or twisted pair wiring. A ring topology is essentially a bus topology with the ends of the cable joined. Each device becomes a forwarding point for the data. Physical connections are typically made using twisted pair or fiber. A tree topology is effectively an extension of the star topology and can be thought of as a cascaded star. There are multiple central devices that are interconnected with each other. The physical connection is commonly made using twisted pair wiring. The logical topology is the manner in which the data flows through the network. The logical paths that the signals or data use to travel between points in the network define how data accesses the network media and transmits packets across the networks from device to device. The physical and logical topologies of a network can be the same, but do not have to be. For example, in a network that is physically shaped like a linear bus, the data travels along the length of the cable. Therefore, the network has both a physical bus topology and a logical bus topology. On the other hand, a network can have physical and logical topologies that are quite different. For example, data sent from PC A to a server can take a different path from the shortest path, as indicated in the figure. Predicting how data travels in a network simply by observing the physical layout is not always possible, so engineers often document logical topologies as well as physical topologies. In this lesson, an introduction to the OSI and TCP/IP reference models is presented, which provides a framework for discussing data communications. We will review the functions of each layer of these models, the use of encapsulation and de-encapsulation to facilitate the transfer of data between these layers, and the role of these protocol models in peer-to-peer communications. Host-to-host communications requires a consistent model for networking. The model addresses hardware, software, and data transmission. Here, the host-to-host communications model is shown. The network devices that people are most familiar with are called end devices. End devices form the interface between the human network and the underlying communications network. In the context of a network, end devices are called hosts. A host device is either the source or the destination of a message that is transmitted over the network. Communication begins with a message, or information, that must be sent from one device to another device. The message then flows through the network and arrives at the end device. Successful communication between hosts on a network requires the interaction of many different protocols. A protocol is a set of rules that govern communications. Networking protocols describe the functions that occur during networking communications. Protocols are implemented in the software and hardware of each host and other devices. Original host-to-host communication models were proprietary. Each vendor controlled its own application and embedded communications software. An application written by one vendor would not function on a network that was developed by another vendor. In the computer industry, proprietary is the opposite of open. Proprietary means that one company, or a small group of companies, controls all use of the technology. Open means that anyone can use the technology and it is free to the public. Business drivers and technology advances are led to a multi-vendor solution. The first step is to separate application software from communications software, which allows new communications technologies to be implemented without requiring new applications. However, the separation still requires a single vendor solution for communications software and hardware. A multi-vendor solution for communications software and hardware requiring a layered approach with clearly defined rules for inter-layer interaction became apparent. Within a layered model, various vendors provide solutions for separate layers. Hardware vendors could design hardware and software to support emerging physical level technologies such as Ethernet, token ring, frame relay, and so on. Other vendors could write software for use by network operating systems that control host communications. To address the problem of networks being incompatible and unable to communicate with each other, the International Standards Organization, or ISO, researched different network schemes. As a result of this research, the ISO created a model to serve as a framework on which to build a suite of open systems protocols. The vision was that this set of protocols would be used to develop an international network that would not be dependent on proprietary systems. As a reference, the OSI model provides an extensive list of functions and services that can occur at each layer. The OSI model also describes the interaction of each layer with the layers directly above and below the OSI model. More importantly, the OSI model facilitates an understanding of how information travels throughout a network. The OSI model provides vendors with a set of standards that ensures compatibility and interoperability between the various types of network technologies that are produced by companies around the world. The OSI model is also used for data network design, operation specifications, and troubleshooting. The OSI Reference Model separates network functions into 7 categories. This separation of networking functions is called layering. The OSI Reference Model has 7 numbered layers, and each one illustrating a particular network function. Although rarely used as an implemented protocol design, the OSI Reference Model is frequently used when discussing network communications due to the clarity of abstraction. Layer 1. The physical layer defines the electrical, mechanical, procedural, and functional specifications for activating, maintaining, and deactivating the physical link for bit transmission between end devices. Physical layer specifications are defining characteristics such as voltage levels, timing of voltage change, physical data rates, maximum transmission distances, physical connectors, and other similar attributes. Layer 2. The data link layer defines how data is formatted for transmission and how access to physical media is controlled. This layer also typically includes error detection and correction to ensure reliable delivery of the data. In a local area network environment, the data link layer contains 2 sublayers that are described in the IEEE-802 LAN standards. MAC is responsible for controlling access to a shared media environment, and there is the logical link control. This control is responsible for the logical delivery of data between 2 adjacent devices. Layer 3. The network layer provides connectivity and path selection between 2 host systems that may be located on geographically separated networks. The growth of the Internet has increased the number of users that access information from sites around the world. The network layer is the layer that manages the connectivity of these users by providing logical addressing. Layer 4. The transport layer defines services to segment, transfer, and reassemble the data for individual communications between the end devices. For example, business users in large corporations often transfer large files from field locations to a corporate site. Reliable delivery of the file is important, so the transport layer breaks down large files into smaller segments that are less likely to incur transmission problems. The transport layer shields the upper layers from transport implementation details. Specifically, issues such as reliability of transport of data between two hosts are assigned to the transport layer. In providing a communication service, the transport layer establishes, maintains, and properly terminates virtual circuits. Transport error detection and recovery, as well as information flow control, ensure reliable service. The boundary between the transport layer and the session layer can be thought of as the border between application protocols and data flow protocols. Whereas the application, presentation, and session layers are concerned with application issues, the transport, network, data link, and physical layers are concerned with data transport issues. The transport layer functions of the OSI model are typically only performed at the end stations in the network and are also a boundary between the functions that happen within the transport network to deliver the data to the host and the functions that happen in data processing. Layer 5. The session layer establishes, manages, and terminates sessions between two communicating applications. The session layer also synchronizes dialogue between the presentation layers of the two applications and manages their data exchange. For example, web servers have many users, so there are many communication processes open at a given time. Keeping track of which user application communicates on which path is important. In addition to session regulation, the session layer offers provisions for efficient data transfer, class of service, and exception reporting of session layer, presentation layer, and any application layer problems. Layer 6. The presentation layer ensures that the information that is sent at the application layer of one system is readable by the application layer of another system. For example, a PC program communicates with another computer. One PC is using EBC DIC and the other PC is using ASCII to represent the same characters. If necessary, the presentation layer translates among multiple data formats by using a common format. Layer 7. The application layer is the OSI layer that is closest to the user. This layer provides network services to the applications of the user, such as email, file transfer, and terminal emulation. The application layer differs from the other layers in that this layer does not provide services to any other OSI layer. The application layer provides services only to applications outside the OSI model. The application layer establishes the availability of intended communication partners, and the layer synchronizes and establishes agreement on procedures for error recovery and control of data integrity. These top three layers of the OSI model are often referred to as the data processing layer because these functions are only performed on the end stations in the network and are often incorporated into the operation system or application program functions. Although OSI reference model layer names are often used, the OSI protocol stack is not the most commonly used reference model. The TCP/IP, also called the DoD model, which was defined at approximately the same time as the OSI reference model, has become the most commonly used reference. The TCP/IP protocol suite is the most popular protocol stack that is used in networks. This protocol specifies end-to-end connectivity, describing how data should be formatted, addressed, routed, and transmitted. Within the set of various individual communication protocols in the TCP/IP protocol suite, the two most important protocols are TCP and IP. The functions of the model are organized into the following four layers. The link layer, also called the network access layer, covers the same processes as the two lower OSI layers, the data link and the physical layers. The network access layer describes the physical characteristics of a link, how access is controlled, and how data is formatted for transmission. The Internet layer provides routing of data from the source to the destination by defining the packet and the addressing schemes, moving data between the link layer and transport layers, routing packets of data to the remote host, and performing fragmentation and reassembly of data packets. The transport layer is the core of the TCP/IP architecture. This layer provides communication services directly to the application processes that are running on network host. The application layer provides applications for file transfer, network troubleshooting, and Internet activities. This layer also supports network applications program interfaces, which allows programs that have been created for a particular operating system to access the network. Information transmitted over a network must undergo a process of conversion at the sending and receiving ends of the communication. The conversion process is known as encapsulation and de-encapsulation of data. The encapsulation and de-encapsulation processes are as follows. The information that is sent on a network is referred to as data or data packets. As application data is passed down the protocol stack on the way to be transmitted across the network media, various protocols add information to the data at each level. This process is commonly known as the encapsulation process. Each layer adds a header and a trailer, if applicable, to the data before passing the data down to a lower level. The headers and trailers contain control information for the network devices and the receiver to ensure proper delivery of the data and to ensure that the receiver can correctly interpret the data. Shown here is how encapsulation occurs and how data travels through the layers. The data is encapsulated as follows. The user data is sent from an application to the application user. The transport layer adds the transport layer header or layer 4 header to the data. The layer 4 header and the previous data become the data that is passed down to the internet layer. The internet layer adds the internet layer header or layer 3 header to the data. The layer 3 header and the previous data become the data that is passed down to the link layer. The link layer function of the network access layer adds the layer 2 header and trailer to the data. A layer 2 trailer is usually the frame check sequence, which uses the receiver to detect whether the data is in error. The physical layer function of the network access layer accesses and encodes the data onto the media. Encapsulation is like sending a package through a postal service. The first step is to put the contents of the package into a container. Next, you write the address to where you want to send the package on the outside of the container. Then you put the addressed package in the Postal Service collection bin, and the package begins its route towards its destination. When receiving messages on a network, the protocol stack on a host operates from the bottom to the top. The process of encapsulation is reversed at the receiving host. The data is de-encapsulated as the data moves up the stack towards the end-user application. When the remote device receives a sequence of bits, the data is de-encapsulated as follows. The physical layer accepts and decodes the data from the media. The link layer checks the trailer, or the FCS, to see if the data is in error. The frame may be discarded, or the link layer may ask for the data to be transmitted again. If the data is not in error, the link layer reads and interprets the control information in the layer 2 header. The link layer strips the layer 2 header and trailer and then passes the remaining data up to the internet layer, which is based on the control information in the link layer header. And then each subsequent layer performs a similar de-encapsulation process. The de-encapsulation process is like reading the address on a package to see if the package is addressed to you and then removing the contents of the package. Each layer of the OSI model at the source must communicate with its peer layer at the destination so that data packets can travel from the source to the destination. This topic describes the process of peer-to-peer communications. During the process of peer-to-peer communication, the protocols at each layer exchange packets of information called PDUs between peer layers. These data packets originate at a source on a network and then travel to a destination. To provide a service, each layer depends on the TCP/IP layer below it. To perform its service function, the lower layer uses encapsulation to put the PDU from the upper layer into the lower layer data field. During encapsulation, each succeeding layer encapsulates the PDU that the layer receives from the layer above, in accordance with the protocol being used. At each stage of the process, a PDU has a different name to reflect its new appearance. Although there is no universal naming convention for PDUs, in this course, PDUs are named according to the protocols of the protocol suite. Data, which is a general term for the PDU used at the application layer. Segment, or the transport layer PDU. Packet, the internet layer PDU. And frame, which is the link layer PDU. The application layer protocol begins the process by delivering application data to the transport layer, which adds the necessary header. The internet layer moves the data through the inner network by encapsulating the data and attaching a header to create a packet. The header information is required to complete the transfer and includes such information as source and destination logical addresses. The link layer provides a service to the network layer by encapsulating the network layer packet into a frame. The frame header contains the physical addresses that are required to complete the data link functions, and the frame trailer contained the frame check sequence. The following key points were discussed in this module. A network is a collection of connected devices that can communicate with each other. A physical topology, which is the design of the physical connection between devices, can differ from the logical topology, which describes the way that the data moves through the network. Host-to-host communications requires the interaction of several protocols and can be described using common reference models such as the 7-layer OSI model and 4-layer TCP/IP model. And during host-to-host communication, each protocol layer at the sender encapsulates the data by adding a header, creating a layer-specific PDU. These headers are read and removed by the corresponding protocol layer at the receiver. This process is called de-encapsulation.